We have another topic that is very important when we start talking about energy methods, which is whenever you have something that instead of, it moves a certain distance, right? A force times that distance. Maybe it's a force times distance per time, per second, per hour, right? And a lot of things run more on a cycle like that. Especially when you talk about thermodynamic devices where it's moving heat at a constant rate, or it's moving an object, maybe on some sort of escalating conveyor, right? Or a train moving at a rate over a certain distance, right? For those, sometimes it makes more sense to do it as a rate problem than a chunk of energy in pound feet or newton meters, right? And so for those, we'll use power. And so power is, like we were saying, it's a rate of energy. It's work per unit of time. So if we divide it by time, then it could still be a force times distance per time. And so we could simply take the work divided by the time. Or another way that we can look at this is if work is force times distance, right? But velocity is distance per time. And instead of having a force times distance per time for power, we could also have a force times distance per time. If you catch the difference there, right? Instead of a force times distance per time, it's a force times distance per time, which a distance per time is a velocity, right? So we can calculate that two different ways, force times distance divided by time or force times velocity, which is kind of nice, especially when we have a velocity easily accessible, right? So power is a scalar, just like the work was defined as the product of the force and the velocity when they're acting in the same direction, right? We might need to make that force into a component that's acting in the same direction as velocity. We know how to do that. So along the lines of units, we could have power in foot-pounds per second or newton meters per second or joules per second, but a horsepower is something that we often are dealing with regular devices and machines. So if you look back in time, 1 horsepower was, I imagine if you're selling your product and you're saying, well, you're using this many horses, you could be using our machine to replace this, however many horses. And so if you can move 550 pounds up 1 foot in 1 second, in theory, that's what a single horse could have done back in the day, right? Or could do. So 1 horsepower is 550 pound feet per second, right? Pounds times feet per second. So kind of interesting unit. Definitely not the cleanest of conversions, but that's what we need to have on our cheat sheet or locked away up here forever, especially if you're a mechanical engineer. I'm sure you'll be pulling that one out from time to time in future classes. Okay. So we could also have joules per second or watts in the other units, right? If we have 1 Newton meter is 1 joule, 1 Newton meter per second is 1 watt. Okay, let's also talk about efficiency. And this is exactly the same as thermodynamics if you're in that class. Your got over brought, right? Is what we like to say for calculating an efficiency. So if we are bringing in some amount of power, whether that's a heat source or maybe that's, an electrical battery providing a certain amount of power, and then that would be your brought, right? We're bringing in that much electricity or heat or whatever power it is, right? And we're getting out a certain amount of power. And it's never going to be 100% efficient. Nothing is, right? Especially when you're talking about combustion and things, there's a lot of heat losses. There's necessary heat flow from a hot body to a cold body. So you can't get 100% efficiency, right? You definitely can't get more than 100% efficiency. Um, but in general, that's what we're doing. How much did we get out divided by how much did we bring? We're never going to get 100% of what we brought to turn into the power that we were trying to do, right? So that will give us a percentage of what that conversion rate was. Okay. We could also do that as simply energy. So this is power in, power out divided by power in. We could just do energy out divided by energy in. That would be the same got over brought. This would be for like a finite amount of time. Power would be for some continuously running cycle or something like that. So there's always going to be friction forces, heat losses, etc. There's never going to be exactly 100% of what you bring converting into the motion that you're trying to create, right? And so because of that, the efficiency is always going to be less than 1. So with that, we're going to now play with the same type of problem, but doing power instead of just energy. And we'll calculate some efficiencies along the way.